Okay, a chemical reaction is a process in which something new is formed. Right? We talked about that being a big indicator for us that a chemical change has happened. So chemical changes take place in chemical reactions. So would you see a change of state in a chemical reaction? A change of state, would that be considered a chemical reaction? No, not going from ice to water, right? Not going from liquid to solid or solid to gas. Those are changes of state. So those aren't new substances being formed. Those are just physical changes. So in a chemical reaction, we have something new that's being formed. Okay? A chemical reaction is made of two distinct parts, and you already know what those distinct parts are called. Does anyone know? Can you think of them? What are they? Products and reactants. Okay? Reactants and products. Reactants are what you start with. Right? You probably already know what products and reactants are. But reactants are what you start with. They are what does the reacting. Okay? Which side of our chemical equation do they go on? The left or the right? Reactants go on the left, right? Those are what you start with. Okay, they are what does the reacting. Products then is what is made, what comes from the mixing of those reactants. So in just an arbitrary chemical reaction, you might have A plus B yields some compound AB, right? These are the reactants. They're what's being mixed, and this is the product. Okay? You don't always have to have the same amount of reactants and products in terms of chemical formulas. Right? And here, in this case, we have two reactants that form one product. So those two are combining together to form one product.
Will you ever have more products than reactants?
Okay, so you could have one that looks like this. AB yields A plus B. Right? We're breaking that thing down into its two distinct parts. So you can have different number of products and reactants. But the thing that's important is that your law of conservation of mass stays intact. So what you put in is still what you get out in terms of mass. It might just be redistributed. Okay. What are some indicators for us that a chemical reaction has taken place? Do you remember some of those indicators? Yeah. And color change, Brogan? Anything else? Temperature change, right? If it gives off heat, right? If it starts steaming or bubbling or boiling, that should be a good indication for us. What's one that's kind of hard to see, but maybe you might smell it? Production of a gas, right? A production of an odor. So a change in heat. Some things will release both energy and light. Those are things, a strong indicator that we've got some sort of chemical change taking place. So it puts off light or energy in the form of heat. Those are good indicators. It produces a gas. Anytime things start bubbling, that means it's producing a gas and those bubbles are working their way to the top. Okay, so if nothing's bubbling when it goes in, and all of a sudden it starts bubbling, that should be an indicator for us that something's happening. You don't have to write like the extra bullets, right? Just change in heat, production of a gas. Make sure you have those down. One of the next ones is formation of a precipitate. Do you know what a precipitate is? What's like precipitation? Right, usually rain, but yeah, what do you think?
Like water is like formed in one little. It just turns into a liquid.
Yeah, okay, turns to a liquid. So in a chemical reaction, precipitate takes on a little bit different meaning. But a precipitate is formed when you combine two liquids and a solid comes out. That's what a precipitate is. Okay? A solid appears when you mix two liquids together. Right? It appears from nowhere. Right? That's not really the case. What's happening here is those ions from each starting reactant are switching places, and they form maybe a solid. Okay? So when you put two liquids in and you get something chunky out, That should be an indication that a chemical reaction has taken place. Okay, and then we talked about color change. So if something colorful appears after the combining of two, whatever, clear substances or two white powders and they become yellow or whatever, color change is a good indicator for us. Okay. Very rarely will it happen that you dump two unknown things together and you're trying to see what happens, right? We'll do it a couple times, but in a lab setting, you're not just going to put two things together that you don't know what will happen already. Okay? So in a chemical equation, we have to put in everything we know. So all of our reactants have to be put into a chemical equation, and all of our products have to be put into a chemical equation. You can't leave out anything. Even if oxygen is formed as a part of our reaction, just because it's oxygen, you can't just leave it out, right? It's going to float away. You can't leave it out of your chemical reaction. That would leave you with an unbalanced chemical reaction, and that won't work. So all of your products and all of your reactants have to be listed in a chemical reaction in order for it to balance, right? What we call balance. Okay, which means that our law of conservation of mass has been satisfied. Okay, it has to contain the correct chemical formulas for all of our reactants and all of our products. So that's why we work so hard with compound naming. Right? If I tell you copper phosphate, right, you need to make sure you know what's the formula for phosphate and can you build the formula correctly. Okay, because if I start to balance my formula like this, CuPO4, and my formula should have been Cu3PO4 2, right? Those are very different substances, and it requires a different amount of each of these atoms. So as we start to balance our equation and we start to look at number of phosphorus atoms before and number of phosphorus atoms after, they should be equal. But if we have an incorrect formula, that means we're going to start with the wrong number of each of those atoms. So having the correct chemical formula is really, really important. Okay? Law of conservation of mass must be satisfied. So that means atoms are neither created or destroyed during chemical reactions. Okay, so this is a lot of words to say the number of atoms you start with on the left has to equal the number of atoms you end with. Okay? It means if there's 5 oxygen atoms in your reactant side, there needs to be 5 oxygen atoms on your product side. And so that's what we're going to work with today is balancing those reactions. So when we start plugging in compounds in a chemical reaction, most of them will be in the form of chemical compounds, not just blank elements. Okay, it's rare that an element like calcium would be put into a chemical reaction on its own. Right? It happens, but not very often. There's some atoms and some elements that if they are in pure form, they can exist by themselves. They cannot exist as single elements. They exist as a pair. And these are called diatomic molecules. Diatomic molecules. These are for elements that are so reactive they just can't exist by themselves. So they pair with another of themselves, basically. Okay? The elements that fall into this category, these diatomic elements or diatomic molecules, I'm just going to tell you because your book doesn't have this page anymore. This is the old textbook. Okay? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. If I start to write a formula and I say nitrogen combines with water, I would say N2 plus H2O yields something, right? You have to internally think about nitrogen as a diatomic, which is why it is N2. Okay, so in order for these elements to exist by themselves, they have to be H2, N2, O2, F2, Cl2, I2, right? They pair with another of themselves and they become a molecule. I left one off there, but whatever. Okay, bromine. They exist as a pair with one of themselves. So that's how they have to exist if they're nitrogen or hydrogen or whatever. Okay, and if you hear them say oxygen gas or hydrogen gas, that's H2, O2, right? Because they are all gas at room temperature. Okay, so if in a problem you see oxygen gas combines with something, it's O2, it's not just O. Understood? Okay, those are called diatomics, right? Because there's two atoms. Symbols used in our chemical equations. You don't necessarily have to write this down, but I want you to be familiar with them a little bit. If you see an S in parentheses, that means we're talking about something in the solid state. You see an L in parentheses, that means it's in the liquid state. You see something with a G in parentheses, that means it's in the gaseous state. And then AQ means aqueous. Does anyone know what that means? Okay, in water, right? But that means that whatever compound we're talking about has been dissolved in water. Okay, and when that's the case, water is not part of our chemical reaction. It's kind of the place where it happens. So water doesn't get put into our chemical reaction for those instances. Aqueous means that our substance has been dissolved in water, but water doesn't play into our chemical reaction. It's just like the house that it happens. Okay? The arrow, the single-headed arrow means yields, okay? And it tells us that we've switched from reactants to products. Okay, so it's kind of like your equal sign. If I put these two reactants together, it's going to give me this. And so that arrow means yields. The double-sided arrow, you'll see a double-headed arrow sometimes, means that it can be a reverse reaction, which means it goes forward, and then as soon as that's done, it goes back. Okay, or sometimes they happen simultaneously. We don't really deal with those, and they won't change the way we solve things right now. In college-type chemistry courses, that will make a difference, but for our sake right now, it doesn't play a huge role. Okay, but it does mean that the reaction can go both forward and backward. So here's just an example of what a chemical reaction would look like. You don't have to write it down or anything. But I want to walk through what's happening here, right? We've got potassium chlorate that's in the solid form, which yields potassium chloride and oxygen gas. Okay, so what's happening here is potassium chloride is being broken down, right? Probably using heat or something like that, or I didn't talk about that, into a solid and a gas. Okay, so you're probably melting it or something. I don't know what they're doing, but they're breaking that down and they're forming potassium chloride, which is a solid, and they're releasing oxygen gas. Okay, and so you notice here that oxygen is not just O, it's O2 because of that diatomic status. Yeah?
So does that mean whenever there's a solid potassium chloride, it's just going to do that reaction? Or do you have to do something?
No, they would have had to put in heat or something like that to make that happen. Okay.
Do you ever have to put the catalyst in the equation?
Okay. Last here before we start practicing is something called coefficients. I want to talk about what does it mean to be a coefficient, right? When you talk about coefficients in math, where do those go? Yeah, with the variable. They go right in front of the variable, right? The number in front of the variable. So in a balanced equation, we need a way to represent that we need more than one of a molecule to help it balance. Okay, and we're going to walk through what that looks like here in a second. But coefficients are the whole numbers that sit in front of our compounds. Okay? So if it says 2H2O, that is just telling us that we need 2 whole water molecules. Okay, we need 2 water molecules to help us balance. Okay, the coefficient also tells us that we have 2 moles of that substance, right? Our scale always works on the atomic level, single atoms or single molecules, and it will blow up to the molar scale. So that 2 tells us that we have 2 water molecules, or when we're looking at a bigger scale, which we mostly do, that means we have 2 moles of water that's got to go into our equation. Okay, 4 total hydrogen atoms and 2 total oxygen atoms, or 4 moles of hydrogen and 2 moles of oxygen. Okay, that's how you solve number of atoms here. Okay, so you distribute that throughout. 2 hydrogens per water molecule times 2 molecules gives us 4, and then 2 oxygen. Okay. We good with coefficients? Easy. Okay, coefficients, oh yeah, we already said that. They represent the relative number of moles as well. Okay, so you don't have to write down the equation, but I want you to just look at it for right now. Okay? As you look at this equation, there's 1 mole of this substance because there's no coefficient listed. That means there's just 1. Okay? How many moles of oxygen gas? 12. How many moles of carbon dioxide? And then how 20 moles of water? 4. And so those coefficients come about from the fact that we have to satisfy the law of conservation of mass, which means on the left side, how many carbon atoms do we have, or individual carbons do we have? 10. That means over here, if we just had CO2, that would only give us 1 carbon atom. That's why we put the 10 in front, to give us 10 carbon atoms. Okay? How many hydrogens do we have on the left? 8 hydrogens. So if I just started with water, I only have 2. That's why we put the 4 there, to make 8 hydrogens. Okay, do you see where that's coming from? I'm going to teach you the process of how to get to this, but I want to show you why those coefficients matter. Right? They're satisfying the law of conservation of mass. So how many oxygens on the left side? 24, 2 per oxygen, and 12 oxygens. So 24 oxygens here. Then on this side I have 2 times 10, which is 20, plus 4, so I have 24 on either side. Okay, that's the reason for the coefficients. Okay, I'm going to walk you through how we get to that point, but I want you to understand why we put in the coefficients. Okay? All right, no, I'm not talking about this, blah, blah, blah. Okay, we're going to walk through the balancing on our own. Okay? So let's say we start with this chemical reaction. H2 plus Cl2 yields HCl. I'll write it a little bit bigger here. Plus Cl2 yields HCl. Okay. Something you should think about when we start balancing equations, you do need to write this down, is that we balance each element individually. We balance each element individually. Okay? And so this is kind of my process for balancing equations. Okay, I list my elements in kind of a vertical list, right? The elements I have, the only 2 elements I have in this whole chemical reaction is hydrogen and chlorine. Would you agree with that? Okay, and then I kind of draw lines on either side. This is my process. You don't have to follow this way, but if it works for you, great. The reason I draw lines on both sides is I'm going to tell number of hydrogens on the left and number of hydrogens on the right. And I want those numbers to match. Right? Would you agree with that? To satisfy the law of conservation of mass, I want those 2 numbers to match. But this is just kind of a working space for me to get those to match. So before I start doing adding any coefficients or anything like that, I'm just going to go through and basically take inventory of how many I have on each side. So how many hydrogens do I have on the left? 2, right? This coefficient tells me there are 2 hydrogen atoms. How many chlorines do I have on the left? 2. Okay, and then how many of each do I have on the right? 1 and 1. So right now those numbers don't match, right? Hydrogen should be 2 and 2, or 4 and 4, or 6 and 6, or whatever it needs to be. Chlorine should match. So what do you think the way is for me to fix this? I add a coefficient. I add my coefficient, and that makes it 2 hydrogens and 2 chlorines, right? So now they're balanced. That means I have a balanced chemical equation right now. Okay, does that kind of make sense? It will get more complex than that, but that's the basic process, and that's what you'll use for every chemical reaction. The good news for chemical reactions is that there is only one correct answer, and you can always get to it. It just might take more than one try. Balancing reactions is kind of like putting together a puzzle, okay? Easy ones like this, no problem, right? But when you have 4 or 5 or 6 elements and 3 products and 3 reactants, then it gets a little more complicated. It might take longer, but the process is the same. Okay, so don't get frustrated if you fill in numbers and all of a sudden it's not working, right? We're going to give you steps to try to work through that. But there is only one right answer, and you can always get to it. Okay? All right, so let's look here. We unbalanced, we balanced, we added the 2, blah, blah, blah. Okay, great. Things to remember, we never add coefficients in the middle of a chemical formula. Okay, once a chemical formula is in the reaction, it does not change. Okay, it does not change. We do not edit chemical formulas. The only thing we do to add atoms to either side is to add a coefficient. Okay, so if we needed, let's say it was H2O, and we just needed another oxygen, right? We don't just do this. Okay, that's not how it works. And we don't just do this, right? Because that's a totally different formula. So if we need another oxygen, we add it to the front, right? Coefficients add to the front. You do not edit chemical formulas at all. Okay? All right, so double check your chemical formulas. It won't balance if your chemical formula is not correct. So if you're in a problem that you had to put in the chemical formulas, like they weren't given to you, that's the first thing you should check if it's not balancing, to make sure your chemical formula is correct. Okay? You never change subscripts in a formula once it's correct. So like we did with our water and hydrogen peroxide example, you don't mix those. Right? Once you know it's water, you don't just add a 2 on it. That makes it hydrogen peroxide. Okay? Last thing I want you to see is that you can reduce coefficients after the equation is balanced if they are all reducible by the same number. Okay, so this means you were balancing your equation and you just went too far. Right? So it might look something like this. 4a plus 2b yields 4ab. Right? If our equation looks something like this, all of these coefficients are reducible, right? Here's the coefficient. Those are all reducible by what? By 2. So it really should be 2 to 1, which you just leave off to 2. Okay? You can leave it empty if it's supposed to be a 1 coefficient there. You can just leave it blank. Okay, or you can put the 1. It's not that big of a deal. But this is a made-up okay. All right. We're going to try this one. Oops. Gave it away. Again, you don't have to use my list method, but that's how I do it. You can use whatever works for you. So I list all of my elements. And then I'll start taking inventory of how many each of them are. So I'll give you time to get it written down, and then we'll start working through it. How many coppers do I have on the left? And on the right, how many do I have? Just 1. The 2 only applies to nitrate. So copper on the right, I just have 1. How many silver do I have on the left? 1. And how many silver do I have on the right? 1. Nitrogen on the left, and on the right, 2. Oxygen on the left, I have 3, and on the right, I have 6. Okay, so I want you to think about just a couple things here. On the left side, oxygen has 3 atoms. Okay, and on the right side, it has 6, which is an even number. There's no way that this could work to be an odd number, right? It has 6. So every coefficient you add to it would just increase it by 6, right? Do we agree with that? But oxygen on the left is an odd number. So the first thing that you need to do is kind of make that match, okay? And in our case, it's really easy to make it match, okay? So I want to get oxygen from a 3 to a 6. What do I need to add? A 2, okay? So if I add a 2, what changes in my column? 2 silvers, 2 nitrogens, and how many oxygens? 6, okay? Now I need to flip-flop to the other side and see, okay, what doesn't match here? What's the one thing that doesn't match? In my list, what's the one thing that doesn't match? Silver. And so how do I make that a 1 to a 2? I just add that coefficient. You notice I'm not doing this, right? I'm not adding the 2 as a subscript. I add it here. Okay, so now I double check them again. 1 copper, 2, 2, and 6, right? That means that's a balanced chemical formula. Okay, the order in which you should start to balance your elements should be basically, or I guess the reverse order. See how silver is by itself and copper is by itself? Those are really easy to adjust. So if you have elements that are by themselves, leave those to the end to adjust. Don't balance them first, right? Because you can add any coefficient on there to make it work. But if you've got elements by itself, leave those to the end to balance. Okay? It's not a huge deal if you try to do those first. You just might be doing more work. Okay? All right, any questions about that one? Okay, what this is telling us is that 1 mole of copper reacts with 2 moles of silver nitrate, and it forms 1 mole of copper nitrate and 2 moles of silver. Okay, on the molar level. If you looked on the atomic level, it would just be scaled down. So 1 copper atom, 2 silver nitrate atoms yields 1 copper nitrate and 2 silver. Okay, that's what those coefficients are telling us. Okay, let's try a couple of these together, and then I'll let you try a couple on your own. Let's do the first and the last one together. So we're going to do these two together, and then I'll let you do the next ones on your own. You don't have to necessarily include the states, solid, liquid, gas. You don't have to include those when you're balancing. Some reactions, balancing, you'll just be able to see it right away and you don't really have to show any work. Some of them will just require more work. Okay. So as I'm taking inventory of the first one, how many aluminums do I have on the left? 1, and on the right I have 2. Bromine on the left I have 2, and on the right I have 6. Okay, so it doesn't really matter which one I do first because these are both by themselves. I'm probably going to go with bromine because that's got a subscript and I can really adjust aluminum to whatever I want. So to fix bromine, I need to go, what do I need to add? What coefficient do I need to have here? 3, right? I want my total to be 6. Okay? So in this case, it really did not matter which one I did first. Right? And then I added 2 to aluminum. That means 2 of each. And 6 of each. So you can add the 1 here or you can just leave it off. It doesn't really matter. Okay? But that's easy, right? Bottom one, we have carbon and hydrogen and oxygen. All right, carbons on the left, I have 2. Carbons on the right, I have 1. Okay, hydrogens on the left, I have 6. On the right, I have 2. Oxygens on the left, I have 2. And then on the right, I have 1, 2, 3. Okay, so here we have another situation in that on the right side, I've got an odd number, and on the left side, I have an even number. So I've got to get my right side to an even number, because this 2 will never become odd, right? No matter what coefficient I add to it, it won't become an odd number. So how could I fix that? Okay, we would eventually have to add a coefficient here. So do you want to do that first, or do you want, I mean, you can follow whatever order you want. Okay? We also have to think about the fact that since oxygen's by itself, we might just want to leave oxygen until the end to balance. Okay, so you can go about it lots of different ways. Okay, so I'm just going to start with carbon because I know I have 2 here, and that means I need what to go here? A 2. Okay, so that changes. On the right side now I have 2 carbons, and how many oxygens do I have? 1, 2, 3, 4, 5. So I have 5 oxygens. Okay, what else do I need to change? Right? Hydrogen now has 6 and still 2 over here. So what coefficient can I add here to make it work? 3. So that means I have 6 hydrogens, and it also affected my oxygens. So I have 3 oxygens plus 4, which is 7. So I'm still running into a problem, right? My oxygens are odd on one side and even on the other side. Can I put any coefficient here to make that become a 7? No, coefficients have to be whole numbers, right? So here's what you do when you get stuck like that. You try doubling. Okay, you just double everything and see how that goes. Okay, so we're at this point where it's not going to work, right? So you can try adding coefficients. You can try going up by ones, right? But if you're at a point where you're just stuck, doubling the coefficients can sometimes help. Okay, so let's just try that and see how it goes. Okay, it might not work, right? This is like a puzzle and I don't have it memorized, but let's just try if that works, okay? So if I double my coefficients and I say 6, 4, 2, and 2, let's see how that goes. Actually, I'm not going to double those ones on the left yet. Let's just see where that puts us if we do them on the right. Okay, so on the right, that means I have 4 carbons, 14 oxygens, and 12 hydrogens. Do you see where those came from? 4 carbons, then 8 oxygens here, plus 6, which is where I got 14 and 12. So now let's go see what do I need to do on the other side. How many carbons do I need on the... I need to add a 2, so that changes my carbons to a 4, my hydrogens to a 12. So now, what can I do? Can I make O2 become 14 oxygens? Yeah, what coefficient does it? 7. Okay? So you could have nickeled and dimed your way to get to that 7 point, right? We could have added 1 here and then another one, then we keep bouncing back and forth. But if you get to a point where you just feel like you're stuck and you can't see the fix, try doubling the coefficients on one side. And then you can go back. And if at the end you overshot it, then you can reduce your coefficients down. Okay, does that make sense? Because sometimes I feel like you just get stuck and you're just not seeing it. That's okay. You either start all the way over or you double it and see if you can work backwards from there. Okay, double one side. It won't do you any good to double everything you've done, right? You got to double this one side. Okay, try the next 2 on your own, those middle 2. Okay, they should be a little easier than that last one. All right, on our potassium bromide reaction, can you tell me the coefficients? Jack, what do you have for the coefficients?
2 and
2,
2.
2, 1?
Wait, 2, 1, 2.
Yeah, agreed? 2, 1, 2. Nicole, what do you have on the next one? Yeah? Not quite? Katie, what do you have? 2, 2, 2, 1. So the difference here is that since we have H2 and H, that means that's 3 hydrogens on the right and 2 hydrogens on the left. So we had to make sure we got that even and odd situation worked out. So is that what we should have had? 2, 2, 2, 1. Okay. Any questions with balancing? Balancing is not necessarily a difficult skill. It just might take work to get to your final answer. Okay? All right. We are going to, we're going to come back to these where we write them out, but we're going to quickly kind of cover the types of reactions. Okay, what are the types of chemical reactions? The first of which is called a combustion reaction. Combustion reaction is when some sort of hydrocarbon, so C something, H something, right? The X and the Y just tell us that those are arbitrary variables, right? C2H4 or C3H7 or whatever it is. That's called a hydrocarbon. So a hydrocarbon combines with O2 to form carbon dioxide and water. So this is an example of a combustion reaction. Okay, and the basic formula for a combustion reaction, you don't have to write down the example, but you might write down this. CXHY plus O2 yields CO2 plus water. Right, that's kind of the base formula for a combustion reaction. So that's what you should write down for what the base formula is, the blank formula. Right, X and Y can be lots of different combinations of subscripts for carbon and hydrogen. So it could be C2H6 or C3H4 or whatever it is, right? Those are called hydrocarbons. But if they combine with oxygen gas and they yield carbon dioxide and water, that's a clue that it's a combustion reaction. Okay, so carbon dioxide and water are always the products of a combustion reaction. Always. Okay, carbon dioxide and water, always the products of a combustion reaction. Okay. Next one is called a synthesis reaction. So when something is synthesized, what's that mean? It's created, right? If we synthesize something or if something is synthetic, that means it's man-made. So when two or more simple compounds combine to form a complex molecule. Okay, so here's the base formula for a synthesis reaction. A plus B yields AB, right? A combination of a cation and anion combined to form that molecule. Okay, so that's your base formula for a synthesis reaction. A plus B yields AB. Okay, if synthesis means to make, what's the opposite of that? Anyone have an idea? To combine, what's the opposite? To break down, okay, which is called a decomposition reaction. So in a synthesis, we put two things together to form a complex molecule. In a decomposition reaction, that means we take a complex molecule and we break it apart. Okay, so the base formula for a decomposition reaction would be AB produces A plus B. So we're breaking. I gave actual examples of all those, but you need to know the base formula for those. So if I say, what's the formula for a decomposition reaction, you're telling me AB yields A plus B. Okay, so those three are really easy to pick out because combustion always has the same products and reactants. Synthesis is when you put two things together or three things together to form a complex molecule. Decomposition is when you break down a complex molecule. So synthesis and decomposition reactions are opposite of one another. Okay, the last two types of reactions are called single replacement. And single replacement means one element trades places with another during reaction. Okay, and here's the base formula for that. It could have little variations to it, depending on if you started with AB plus C or whatever, but that's kind of the basic formula for a single replacement, is that one of our elements switches places. And single replacement reactions are a little harder to see, I think, when you're looking at a regular chemical reaction for that. I think they're a little bit more difficult to see, but you need to know what that kind of base formula is for that. Okay, double displacement or double replacement is the easiest to see, I think. Okay, or one of the easiest to see. And double replacement is when the anions and cations completely switch places. So anion and cation plus anion and cation, and they just switch. Okay, these are also called a precipitation reaction. Okay, this is when we form a precipitate most often. And that's the formula for double displacement. Okay, so a double displacement, sometimes I call displacement, replacement, displacement mean the same thing, but they cannot have any variations, and this is why. When you have your compound, it's always cation, then anion, right? Cation, then anion. So in any chemical formula, right, the positively charged ion always goes first, and then the negatively charged ion, right? When you make a chemical formula, it always goes positive, then negative. Would you agree with that? Right? It always goes positive and negative, or goes left to right on the periodic table. So when we form our new compounds, it's got to be a positive that combines with a negative, and it's got to be a positive that combines with a negative. So that's how our new products are formed, which is where we got CB, not BC, right? Because C is the positive and B is the negative. A is the positive and D is the negative. So it's important in how those are written in our final formula, right? A is the cation, so it gets paired with D, which is an anion, and it's written positive, negative. Then B pairs with C, but it's written CB because C is the anion, C is the cation, and B is the anion. Okay, so we have to write them correctly. So it's always outsides get paired and insides get paired, okay, in a double displacement reaction, and then you just need to make sure you write them correctly. Okay, so here in this last reaction, you can see lead is the cation, nitrate is the anion, potassium cation, iodide anion. So if we predict our products, it should be lead iodide, which it is, and it's potassium nitrate, which it is. Okay, so you need to make sure that when you build those new formulas, you are balancing them correctly. So although we have 2 nitrates here, we don't necessarily have to put 2 nitrates with potassium, right? That's where that coefficient comes in. So you balance the formula after you build those new final compounds. Okay?